Hello everyone. My name is Aditya Prabhu. I am a master student at the University of Regensburg, and this is a very short and basic explainer about some of these terms pertaining to groups, namely polycyclic groups, nilpotent groups, and solvable groups. And I will try to sort of give some relations between who's who of these three terms. Yeah, so we shall start with the most basic definitions, of course, which is the one for nilpotent group. And of course, you all know this, but a nilpotent group is some group which has this sort of a terminating commutator series. So if you start with the group and then you take the commutator of the group with itself, and then you take the commutator of the group with this first commutator and so on, it turns out that these subgroups are normal in the previous one, and you get this series of subgroups. And if this terminates after a finite number of steps at the identity subgroup, then you say that the group is nilpotent. And we shall see another equivalent definition of this by via group extensions. So an exact sequence of groups like this. So if you have the identity to some group K, which is called the kernel, to your group G, which you say is the constructed group extension, to some other group H to 1, this sort of a exact sequence of groups is called a group extension. And so we shall give a recursive definition of nilpotent groups. So we shall say that the trivial group is nilpotent of type 0, and then we say that any extension of a nilpotent group of type R by any group which lies in the center of the thing you're constructing, we say that that is a nilpotent group of type R plus 1. So for example, a central extension, and central extension means only that the kernel in this exact sequence, this K, lies within the center of G. That's all. Okay. So we shall say that any central extension of a nilpotent group of type 0 is a nilpotent group of type 1. And then we go and extend these nilpotent groups of type 1 centrally again to get nilpotent groups of type 2, and so on. And then all of these groups will be precisely what we get as nilpotent groups via this definition. So these two are equivalent. Okay, cool. So what would be some examples? Well, a very trivial example, of course, is abelian groups, right? So any abelian group, and this is just the most standard one as well, has the commutator subgroup to be trivial. So any abelian group is nilpotent. So in some sense, you can say that nilpotent groups are these approximations of abelian groups, because you're saying that you're extending a group centrally by something else, right? So it's, in particular, it's an extension by an abelian group, and moreover the abelian group is embedded centrally in the thing that you construct now. So yeah, in some sense this is trying to go towards, this is trying to hint towards G being somehow weakly abelian. And well, so there is another type of thing that we could do, which would be to define solvable groups. And well, a group is called solvable if this particular series of subgroups terminates at the identity, right? So how is this different from before? Well, it's just that before we made the commutators have elements from all of G at each step, yeah. But here we do not do this. We just take the previous subgroup, whatever it was, and then you take the commutator of that with itself, and then so on. Yeah. And equivalently, well, again, just to get a flavor of the extension arguments, we can say that the trivial group is solvable of type 0, and then we say that any extension of an abelian group by a solvable group of type R would be called a solvable group of type R plus 1. So if you take this abelian group here and you extend it by some solvable group which is inductively defined here, then whatever you construct would be called a solvable group of type R plus 1. And great. So this is what that definition would look like here. And there is another thing which we call polycyclic groups, and I had not heard of these before. So a possible way to define them is this way. A group is called polycyclic if there is a series of subgroups which is finite, and moreover the next one is normal in the previous one, such that the successive quotients are cyclic. Yeah. So this is somehow more of a condition in the structure of the group. We are saying that the group is such that you can quotient out a part of it, let's say G1, and once you quotient out by G1, whatever remains is cyclic. And the thing you quotiented out by again has the same property. So you can quotient out by something in there which leaves only a cyclic thing back, and then you can keep doing this until and in a finite number of steps you would be at the identity. So equivalently, we could also define polycyclic groups this way. We can say that the trivial group is polycyclic, just as before, and then we say that we can extend a polycyclic group of type R by a cyclic group to get a polycyclic group of type R plus 1. So for example, you could have the trivial group right here, and you extend it by some cyclic group, and whatever you get would be a polycyclic group. And then you take polycyclic groups of type 1 and then you extend them by cyclic groups again, and you get cyclic bicyclic groups which are also polycyclic, and so on, so on, so on. Yeah. One important observation at this point would be that polycyclic groups are finitely generated, because you're saying that polycyclic groups are obtained through a finite number of extensions of cyclic groups by cyclic groups and so on. And there is this property that you can show about group extensions, which is that if you have such an exact sequence and K and H are finitely generated, then well, due to exactness, you know that G mod K is isomorphic to H, and then you can find a generating set which is finite for G given the generating sets for H and K. Yeah. So polycyclic groups are finitely generated. So this is pointing towards the fact that they have nice structure, right? It turns out, moreover, that they are slender, so they have this property that all of their subgroups are also finitely generated, right? And this you can show again inductively by saying that extensions of slender groups by slender groups are slender themselves. And so this kind of hints towards the fact that polycyclic groups are groups with really nice structure, right? So they are slender, they are finitely generated, they are residually finite, and so this is quite a nice class of groups, right? And it also turns out, well, as we know, that finitely generated abelian groups, they have this really nice structure, right? So they come up as, so you can realize whatever this is, this direct sum of a bunch of z to the r's plus cyclic groups as successive extensions of cyclic groups by cyclic groups. So you can prove that this sort of a thing would be polycyclic. So it turns out that abelian groups have this nice structure and they are polycyclic. So in some sense, polycyclic can also be viewed, at least in the case of finitely generated groups, as an approximation of abelianity, as we would nilpotency or solvability, right? And now I will show you a schematic to see where all these groups lie with respect to each other, right? So we have in the middle the class of abelian groups, right? These are the ones we know and love, of course, and this is only within the class of finitely generated groups, so we are not looking at things like Q and R and so on. Yeah. So we have abelian groups, and any abelian group is nilpotent, trivially, and any abelian group is solvable and also polycyclic and so on. So you can prove this. So you can prove this class of inclusions quite nicely. Well, abelian inside nilpotent is clear. Nilpotent inside polycyclic, well, this is a theorem of Hirsch. So Hirsch has this theorem that finitely generated nilpotent groups are polycyclic. And polycyclic groups are solvable. Well, that's just trivial. You can really just look at the definition and see that cyclic by cyclic extensions come under the class of abelian by abelian by abelian extensions. So this is trivial, and we shall see some examples to see that these inclusions are indeed strict, right? So you can prove that the dihedral group on 8 elements, this is a nilpotent group, but it is not abelian. This is completely doable. You can check this by hand. Polycyclic but not nilpotent. So now you want something that lies in here but not here, and not here. So one example of that would be Z semi-direct Z. So you look at this group extension. You have 1 to Z to Z semi Z to Z to 1, right? And assume that this extension is split, meaning that there exists an action of this copy of Z right here on to this copy of Z, and there's only one on trivial action, so you can find it and then whatever this group extension defines is called a semi-direct product, and this, it turns out, is not a central extension, and this group does not arise as any central extension, so this is not nilpotent for sure. So this group is not nilpotent. You can also prove it via the commutator definition if you prefer that. And yeah, so this group turns out to be not nilpotent, but it is polycyclic because, well, this is just a extension of a cyclic group by another cyclic group. So somehow it goes further away from abelianity because it has this big it goes further from abelianity because it is this big subgroup here which is not central. It's not going to commute with everything. Yeah. And something that is solvable but not polycyclic, so something that lies here, is the Baum-Slag-Solitar group on these parameters 1 and 2, which conjugates one of the generators to the square of itself by when you conjugate by the other generator. Yeah. This, it turns out, mysteriously is the semi-direct product of a group which is isomorphic. So the subgroup generated by Y, if you take the normal closure of this, then it turns out to be the group of dyadic rationals, and there is an action of the other generator on this. Well, again, exactly this thing right here. It conjugates this sort of an element to 2 to the m times that element, and yeah, this it turns out this is a semi-direct product. This is solvable, well, because this arises an extension of this by this, right? So again, an abelian group by an abelian group, this would be solvable. So yeah, that is why this group is solvable. But it is not polycyclic, well, because we saw that polycyclic groups have nice structure and they are in particular slender. So when polycyclic groups are slender, this would be a subgroup of this polycyclic group, but this is not finitely generated. Dyadic rationals are not finitely generated, so this would be a problem. And yeah, so it kind of goes to show the fact that solvable groups can have really complex structures, but yeah, polycyclic ones will have nice one. So that was all I wanted to say. So just a little bunch of facts about all these things, and yeah, thank you, and I hope you have a great day.